So let's go to pressure fundamentals. So we have your hydrostatic pressure. So hydrostatic pressure. Okay. So our hydrostatic pressure, which is defined as the barometer, or where the barometric pressure or atmospheric pressure so we have also, this is the atmospheric, no? So, atmospheric pressure, where can be simplified as if you have your barometer here, then we have here, so you have your fluid here, the mercury, then I have here the mercury of the fluid, then the acting pressure, which is showing atmospheric pressure. Okay, or this can be as pwede ring liquid. Okay, so that is acting on that one. Pwede rin palang water. Okay, so where your atmospheric pressure is equal to the pressure surrounding, which is equal to the specific weight times yung height. So may sinasabi niyang height. What is the height? So the height is usually this one. Taking this one, this is now your height. Okay, so this is in the forms of PSI. The unit can be the unit is PSI, and you have Pascal. So notably, so in machine design, so in machine design, and strength of materials and strength of materials calculation are all in gauge pressures are used for calculations. So for calculations, for your calculations, gauge pressures are always used. So take note of that one. Gauge pressures are always used. So take note of that one, no? So baka may if you forgot, you convert it to the absolute, then substitute nyo sa equation ng mga bearings, so acting on the surfaces for the strength of the materials, or acting at once. So yun ang ang differential niya when you're making calculation for fluid tawag dito machine design and strength of material, and also in thermodynamics and fluid mechanics. Take note, you will notice that class na thermodynamics and fluid mechanics are always magkasama in terms of tawag dito lecture. So there are part that is in fluid mechanics that is also part of the thermodynamics, because this is a dynamics, and also the properties of fluid, which is also a property that is used by the thermodynamics, no? So there are palaging magkasama. So take note of that one. So that's why you will notice that I'm discussing that is pressure, which is already in the fluid mechanics, but in the thermodynamics needed also the fluid mechanics in order to cope up with the design of its fluids. Okay, so we have reviewing the thermofluids, so hydrostatic pressure principles. So we have your hydrostatic pressures principle, no? So we have hydrostatic pressure. So take up this one, hydrostatic pressure is independent So we have your hydrostatic pressure principle. So define independent of the shape and size of its container. So at equal depths at elevation acts at equal intensity. So illustration ng kanina principle, we have this hydrostatic paradox, no? So if you can see, we have here your fluid here. Then we have different shapes of container. Okay, so the elevations 1, 2, and 3 are equal. So the pressure acting at P sub 1, so yung P sub 1 mo is equal to P sub 2 and equal to P sub 3. So that will be defined as the hydrostatic paradox. So pressure is not independent of the shape and size of the container. Okay, so that defines that one. Okay, so we have the Pascal's law. So pressure is a scalar quantity. So for confined pressure may be transmitted without loss to any point within the container. And also we have liquids are basically incompressible. Okay, so that one defines. So if we have a container like this one, no? So in point 2, we have it here, your point 2 here. The pressure is acting doon paikot. So it's acting all around the object at point 2. Okay. So we have your elevation, which is your Z. Okay. Now, so the constant here, we have the constant here. Constant here is the specific weight. Okay, so we have your pressure at point 2 is equal to pressure at 1. So that will be plus minus the specific weight times the we call this elevation. So usually pressure 1, that is yung pressure on this one we have here, or we can change that one to the change in pressure. So since we transfer that one, it will be plus minus the specific weight times the Z value, where is positive if that is depth. So and also if that is in elevation, so that is negative. So change on it depends on the atoms. So we can also change that one if you have your variable, no? Have your variable, we can differentiate that one as plus minus. So kung variable siya, the specific weight, then you have the differential height to get the if you have a variable changing elevations, so we can get the pressure differential of the pressure of that one. So let's go to the ideal gas law, so or the equation of state, the point function, and also the can be called also the general gas law. So those terms were used to describe the equation PVMRT. So the ideal gas law. Sometimes it will be called that as equation of state or the point function, and tinatawag natin sometimes it's also called the general gas law. So where your pressure, your P, is the absolute, defined as the absolute pressure, no? Then your V, so that will be the volume of the gas. Okay, then your M will be the mass of the gas. So where your T, it will be the absolute temperature, so take note. Then your R, we have your gas constant. Now for the unit in English, so we have your absolute pressure, so that will be PSI, absolute. So in SI, it will be either QPA, absolute, or PA, absolute. So the volume of the gas would be cubic feet, and this will be cubic meter. Mass, it will be pound mass, and then the one SI, it will be kilogram mass. Absolute temperature will be degree Rankine, and you have your Kelvin, no? So the R constant, it will be foot pound force divided by pound mass degree Rankine. SI will be kilojoule kilogram Kelvin. Okay, so we have the variant form of the equation. So that can be expressed as P BT, which is equal to MR. This is, you have your constant here. So it's constant. Okay. Then the first variant, we can also have the first variant. So that will be P1 B1 T1 is equal to P2 B2, then T2, which is equal to MR, then you have your constant. So it's constant. Okay. Then so these laws represent the general gas law under the specific conditions. So we have one. So at the pressure is constant, so we have isobaric, or sometimes they call it isopistic. Okay. So we have your P1 B1 T1 is equal to P2 B2 and T2, so cancel out, we have your constant here. Okay, so it will be, since your P is equal to P1 is equal to your P2, so it will be B1 now T1, that is equal to B2 T2. So they call it now what we call the charge law. Okay. Then we have number 2, which is your V is constant. So call it isometric, no? Or sometimes it's called isochoric. Okay, so sometimes it will be babanggitin lang sa problem, isochoric, so you must know what type of process is that one. So establishing the relationship here again, P1 B1 P2 B2. So since it is constant, so we have now your P1 T1 is equal to P2 T2. So they call it now, this is called as Gay-Lussac's law. Then we have number 3, where the temperature is constant, so the process is isothermal or isothermic. Sometimes it is called isothermic. So where your T is equal to T1 is equal to your T2, so establishing the relationship, so cancelled out, we have P1 B1 is equal to P2 B2. So this is now the Boyle's law. Okay, so we have the second variant for the ideal gas equation. So you have your PB mRT, so it can be expressed as mass over the volume, which is equal to your P over RT, which is now equal to the density. So this equation, so use in finding density of gas. For the third variant naman, so if mass is not given, so there is no mass given, so we have then more of the gas will be specified. More of the gas will be specified. So we can use PB is equal to 8.314, where your N times T. So this is for SI. Now for English, so then will be 1545 N times T, where your N is the number of mole of gases, number of mole of gases. Then your R, so usually R is universal gas constant, no? Or your R, universal gas constant. So that is equal to 8.314. That will be kilojoule per kilogram mole Kelvin. So for SI, then it is 1545 foot pound force pound mole degree Rankine for English. Then we have the definition of mole, which mole is the molecular weight, or sometimes the mass of a gas, where your mole will be mass of the gas divided by the molecular weight. We call it moles. So we call it moles. So we have thermodynamic systems. So systems, anything that one wishes to study, provided there is a boundary. Okay? Boundary, so that will be a fixed or moving. So that will be a boundary is either fixed or moving. Okay? So for the thermosystems, we have open system. So that is control volume siya. Okay. Then open system. Then we have closed system. Closed system with is a control mass. Then we have your isolated system. Okay. So those are the type of the system that we have in thermodynamics. So laws governing the thermosystem, we have laws of governing thermosystem. So we have first law, so law of conservation of mass. Law of conservation of mass. So mass is indestructible. Provided no nuclear process is involved. No nuclear process is involved. Okay. Then we have the relationship that mass entering is equal to change in mass. Change of mass within the system. Change of mass within the system plus mass leaving the system. Okay. Or we can rewrite it in equation that the mass in is equal to your change in mass plus the mass out. Okay. So that is the macroscopic. Okay. Macroscopic. Then 2. So we have first law of thermodynamics. So we have your first law of thermodynamics. So law of conservation can be described as the law of conservation law of conservation of energy. So energy cannot be created energy cannot be created nor destroyed but it is only transformed from one form but it is only transformed into one form to another. One form to another. Okay. So it can be shown in equation that energy entering is equal to the energy change of energy within the system plus the energy leaving the system. So we can rewrite it in the equation. Energy in, it will be the change in energy plus the energy out. Okay. So to summarize, so the mass in is equal to your mass change in mass plus the mass out, okay? Where your energy in is equal to change in energy plus the energy out. Okay. So rules, if take note, if mass in is equal to mass out is equal to 0. So they call it no mass enter or leave the system. So this is no mass enter or leave the system. So and if energy in and the change in energy plus the out, okay, we have energy interaction occurs. So we have energy interaction occurs, so and causes boundaries. Okay. So then the system is called closed system. So we can say that then we can call it that the system is a closed system, is a closed system. So it undergoes a non-ion process. It undergoes a non-ion process. Okay. So we have another name for a closed system. So another name for a closed system we call it non-flow system. So that is non-flow system or control mass. Okay. Now number 2, so if the mass in is equal to mass out, then your change of mass is equal to 0, and the energy in is equal to energy out, or the change in energy is 0, then the system is an open system. So then the system is open, or open system. System, it undergoes, the system undergoes a steady flow process. Steady flow process. Okay. So another name for that one is, we call it, another name is, we have call it an open system or steady flow system, o tinatawag din natin is a control volume. Control volume. So for number 3, so if the mass in and your mass out is equal to 0, and we have your energy in and energy out is equal to 0, so we have no mass crosses the boundary, crosses the boundary. And we have no energy crosses, no mass crosses the boundary, and no energy. No energy crosses the boundary. Okay. Then we have called it an isolated system. So the system is called isolated. So for illustration, so we can illustrate it as for your control mass. Okay. So we have, sample is a piston cylinder arrangement, no? So that is a sample of a control mass. So we have a piston and a cylinder arrangement. Then you have your work, non-flow, acting on your piston. So you have your ideal gas here. Then you supply a heat in order to expand. So as you expand, you produce a non-flow work. Okay. And it can be, you have here mass in is equal to mass out, which is equal to 0, since there is no crossing the boundaries, no? So mass in, mass out is contained. So you have your ideal gas here, staying here. Then you have energy in is equal to the change in energy plus the energy out. Okay, so you supplied energy. So how do we supply energy? By means of your heat supplied is equal to the change in internal energy, which is mCp delta T, plus as you produce a heat, you supply a heat, you produce a work non-flow. So you have your work. Okay. So that is the sample of a control mass. So simple energy equation we have. So it is a non-flow energy equation. Okay, or NFEE, non-flow energy equation. Then if we go to open system, for open system, open or steady flow system, so that is control volumes naman, that's what we have. So laws governing the control volumes, you have mass in is equal to your mass out, okay, where your energy in is equal to energy out. So steady flow energy flow can be, so that is steady flow. So it can be classified as, for steady flow, it can be classified as compressible flow, sample niyan is gases. Okay. Then we have non-compressible flow, sample niyan is liquids. Okay. So continuing here, your steady flow for the compressible flow. So let's draw a sample here of an orifice, or we call this concentric pipe, a reducer pipe. Okay. So we have your area here, then we have your volume going here, then we also have the specific weight over here, where your mass in, so this is an illustration, the mass out is equal to the mass flow rate, so that one, which is constant. So the mass in and the mass out is constant, so it means it is continuous. Okay. So for non-compressible, we have so for compressible, we have volume continuity equation also. Okay, so let's go back here for the control volume. So let's discuss the control volume. So for the control volume, so that will be all power industrial plant equipment. Okay. So for control volume, so that will be all power and industrial equipment are considered open system, so unless otherwise being specified. So we have sample, and we have your turbine, compressor, heat exchanger, then also nozzles. So there were those are the examples. So where your mass in and your mass out and your energy in is equal to energy out. Okay. So for the volume continuity equation, for this one we have the equation volume continuity. Volume continuity equation, we have your Q, which is your, or sometimes it can be expressed this one, that will be area times the specific volume, which is equal to area 1 volume 1, or this is cubic velocity. So this is the velocity. Okay, below area 1 times the velocity 1, which is equal to area 2 to velocity 2. So continuity equation. And also for the mass continuity, then we have the mass continuity equation. We have the mass flow rate times your density times the volume. You have your density times the velocity, or the mass flow rate now is equal to the density area 1 velocity 1 density 2 area 2 velocity 2. Okay, so that expresses the mass continuity equation. So we have here a turbine, or it can be expressed as a turbine or the expander. So we have your mass in, sample illustration, then control volume, mass in, and you have your mass out. Okay, so this is a sample of control volume. So I have here the sample of a compressor, no? So you have your work by means of we call this electric motor to produce a work. Then as you produce this work, you compress the air, you have suction, you have your mass in, and you have your mass out. So you have your here, air is being compressed and it will be pushed out. Then those work produces heat. So usually pag ginawa kami yung compressor, you will feel the heat being produced as you work is being done by the system. So this is one of the example now. Okay. So control volumes or steady flow energy equations. So we have your mass related formula. Have your mass related formula. Again, that will be mass flow rate density times the area times the velocity. Okay, or it will be density times the area, and then you have your specific weight. Okay. So other variant that will be for this equation, variant form. So that will be density 1, area 1, velocity 1 is equal to density 2, area 2, and velocity 2. Okay. So let's go to the energy forms. So this is your control volume. Okay. So this is what we have here is a control volume. Then we have your workflow 1, potential energy 1, kinetic energy 1, internal energy. So then we have your mass flow rate entering to the control volume, and you have your mass out going out to the control volume. Then we have your workflow 2 and potential energy 2, kinetic energy, and we have also the internal energy 2. Then you have a supplied heat and you produce your work. So your energy forms, we have two kinds, no? We have energy forms. We have two kinds of energy forms. So one is stored energy. So we have stored energy. Okay. Then we have energy in transition. Energy in transition. So stored energy, we have your PE, so that will be potential energy. Potential energy. Then we have kinetic, KE, kinetic energy. Then we have your internal energy. Then we have your WF, that will be the workflow or flow of work. So energy forms that are, we call it, and these are energy forms so that are dependent on mass. So they are dependent on mass. Then we have your energy transition. So this will become your heat. So your Q. And we have your work, which is your W. So that is energy that flows. So they are independent. So independent of mass. Okay. So let's start with the stored energy forms. No? So we have your stored energy forms. So we have potential energy. So potential energy, so that is energy due to gravity or due to body's position or elevation. So from the datum, it will be from the datum. Okay. So it is illustrated or by a simple object. So you have your mass, then we have your weight here, then you have your ground sa baba, no? Then we have your elevation or your datum, so we have your Z. So the equation for potential energy, that will be is equal to mass times the gravity times their height. Okay, or this can be expressed as the weight times your elevation. So the units, it will be for your mass. Okay, so the units need for your mass So for your mass, we have for English it will be foot, pound. Sorry. So this will be your PE in unit for English. So it will be foot pound force for SI. So we have Newton meter. Okay. Then for the mass, it will be slug SI in English. Then it will be kilogram for SI. Then for your elevation, so that will be feet or meter. Then for the gravity, it will be feet second squared, then meter second squared. So for the weight, the unit will be pound force, and we have the Newton. Okay, so that will be the units. So take note of that one.